This video will continue our discussion of life in the universe and the search for it, and begin by talking about habitable planets. For a planet to have life on it, we would think that it has a stable temperature, where we have the liquid water, and could be supplied from the star or perhaps from the interior of the planet. The version we have on the Earth is from our star that is responsible for our surface temperature primarily, although our interior is warm. If we did not orbit a star, the Earth would cool off rapidly. So having a stable temperature around a star is good. Why is water in favor as the liquid where life would thrive rather than liquid methane or liquid ethane or liquid ammonia? Water has advantages over these other compounds. One advantage is that it's in a liquid state over a broad range of temperatures. This gives us a wider habitable zone where a planet could be located and still have the liquid water condition. If we have liquid methane, that's a narrower temperature range, etc., for the other molecules. Also, water is in its liquid state at a higher temperature than these other molecules, and a higher temperature helps promote chemical reactions that are useful for deriving energy to energize life. And we have a situation, water is a really unique liquid. As lakes cool down in the winter time in north central United States, the layer of ice forms on the top of the water. Water has lower density as it freezes, and the liquid water remains at the bottom of the lake, if it's a large enough lake, and the fish survive. So, not saying I want to live like a fish underwater, but water allows that to take place. It forms an ice layer at the top and insulates the liquid from the cold air. Also, water is a known molecule throughout the universe. It is in abundance. So it's available, it's a resource. And water is a property of not changing temperature much as energy goes into the water or energy comes out of the water. So it moderates the range of temperatures that an organism would undergo. It makes our body temperature more stable. Another example would be in January, where's the more popular vacation spot? Nebraska or Hawaii? It's January in both places. Nebraska is a lot colder. We don't have any large bodies of water near us that moderate the temperature. Hawaii, out in the ocean, large body of water near it, and the temperature gets moderated. There's more to it than that, but Nebraska is a very nice place, but where I grew up, but not quite the vacation spot. Okay. Some other considerations on life. Astrobiologists tend to lean towards searching for carbon-based life forms rather than, say, silicon. Carbon has more stable molecules than what forms with silicon. And again, we're looking at the population 1 type stars that have resources of elements heavier than helium. We would look probably for life on a solid planet rather than a gas planet. With a solid surface, the liquid can accumulate into pools on the surface and be available. A little more of a resource there. We would like the planet to have an atmosphere. That moderates the temperature of the surface of the planet. The atmosphere acts like a blanket at night and keeps us from dropping temperature too much. The weather forecast in January, clear and cold. But if the skies are cloudy, it doesn't get as cold at night in January in Nebraska. Atmosphere also plays a role in shielding us from radiation. The natural radiation that's in space and encounters a planet, the atmosphere blocks some of that. An atmosphere also creates a pressure at the surface that allows liquids to pool up and not disperse, not evaporate. It's nice to have a large moon for the planet, and just starting to get to the conditions where astronomers are not only finding planets around stars, but in the getting to the technology level where moons can be identified around planets, around stars. Not much of that yet in 2015, but look for that in the future. Our moon does play a role in stabilizing the direction of our rotation axis. It makes our planet, again, a little bit more stable, and keeping temperate places on the Earth temperate for long periods of time. And then plate tectonics, sort of an active, semi-active planet. We don't want volcanoes everywhere, but having this liquid core at high temperature and the rotation of the Earth generates a magnetic field that plays another role in protecting us from radiation from space. And the volcanic activity brings us up not only atmosphere, carbon dioxide and other gases as well, but also brings up a supply of minerals, again, resources to be used. So those would be kind of the characteristics we look for in a habitable planet. Again, the Kepler spacecraft that will be described in a future video has found Earth-sized planets, a little bigger, a little smaller, in the habitable zones of their stars, where liquid water can be expected to exist. So 3 planets here close to the star, not in the habitable zone, too hot, but 2 planets in Kepler 62 that are in the habitable zone. And some other, these are artist sketches, these are not photographs of the planets, but Earth size down here, and then the Kepler spacecraft is detecting objects comparable to the size of the Earth. Now, again, new technology coming into play and capabilities. It's becoming possible for the detection of biomarkers on these exoplanets that have been discovered. And a biomarker itself is an indicator that there's life activity taking place. Telescopes on the Earth can isolate absorption lines in the spectra that are created by the planets and the planet's atmosphere, and are gaining capabilities to look for these biomarkers. We can't go there ourselves to sample the gases in a planet's atmosphere or land and see how much water is on the surface and so forth. So this is done remotely, studying the light that comes from the planet, and as the planet moves in front of its star, it's going to absorb some of the light from that star through its atmosphere. And there are some planets also who are directly imaged by telescopes and can be investigated for what their atmospheres and surfaces might be like. Now, some biomarkers. Oxygen. Oxygen is not long-lived in an atmosphere where there is no life. So our plant life here on the Earth is putting oxygen continuously back into the atmosphere. Oxygen likes to combine with other elements and would be removed from the atmosphere. I don't remember the timeline for sure, 500, 700 years. A lot of oxygen would be gone if there was no plant life on the Earth. Another biomarker is methane. Metabolism produces methane, and if that's in great abundance in an atmosphere, that might be an indication there's life there. Pollution. So unfortunately, if these other civilizations get going and get into an industrial age and don't restrain themselves in using up their fossil fuels and so forth, we might see similar pollution in their atmospheres as what's in our atmosphere. So telescopes are used to study these absorption lines and look for the biomarkers, and also at the same time look for evidence of water vapor, be an indication of clouds and some type of weather that the planet might have. So biomarkers, and oxygen is really a big one, as to we know it's important for life, and we'll look for that. So these absorption lines, and this slide is really not detailed enough for you to get a good picture of this, but there are instruments that are capable of looking for the absorption lines that are the biomarkers, and that research is underway. Now, a little bit, we talked about evolution in a prior video. I'd like to give a few words on intelligent design, try to give a balance of viewpoints here. So the intelligent design foundation is that the universe and life that we're here indicates a creator. So, oops, sorry about that. We'll go back here. So we have a universe, and As astronomers and physicists look at our universe, they would agree that if we'd have some changes in the constants and equations that deal with the force of gravity, the force of electricity, strong nuclear force, and so forth, um, there would be a big change in the universe, and perhaps too much of a change for life to exist. If the way that physical laws behave did not allow stars to form, nuclear actions to release energy and create starlight, um, you know, we'd have a problem with temperatures that would have liquid water on planets. It may be a situation with different constants that atoms would not form. The protons would not stay near other protons, or molecules would not form. And if life existed, it would be much, much different than what we know, because we really are built with atoms and molecules giving us our life systems. How about complex life? So there are many cases where the life that exists has multiple pieces that work together, and many people have difficulty imagining how all these got to be in place if evolution would just promote one at a time. It seems that there's life evidence that multiple pieces got established at once. There's also good evidence in the fossil record that the life on Earth was not a uniform, smooth process, but there were spurts of growth of life and times of great change. And evolution is kind of based on slow changes going throughout the process. I'm not an expert on evolution, but in my view, the intelligent design works better in matching these spurts of life in the fossil records. What about life on Mars? Many years ago, there was a meteorite discovered from Mars, identified as coming from Mars, and this is a microscopic view of that, and people were struck by, kind of looks like a little worm here in the rock structure. Other people would point out that this structure can form chemically, just from chemical processes and kind of bubbling of material. So this is not proof that there's life on Mars. That search is going to go on, as it should, to identify our solar system better and where life is possible, and guide us in looking for life on other planets. But at this point, no evidence for life on Mars. I just want to give you a few images here of the Hubble telescope being used to image exoplanets. And when the Hubble goes back and takes a photo in a different year, these planets move positions. So they're in orbit around the star. The central star has been blocked. Or over here you kind of get the first picture. But there are techniques to remove the light from the central star, and then you can see the orbits of the planets, and quite a bit bigger than where the terrestrial planets are in our solar system. Their orbits are bigger, but telescopes are getting this capability to image planets, and again plot out their orbits as to what's proceeding, and potential habitable worlds where in the habitable zone, and in the cases of being similar to Earth size, hopefully having a solid surface and water. More of that needs to be investigated. And this slide is a little out of date. It's from 2011, but now in 2015, the Kepler satellite has identified about 4,500 exoplanets. They've not all been confirmed as exoplanets, but that many candidates, and there are many habitable type planets in their habitable zones and size of the Earth. So this search for life will continue. So you ought to write down your own questions and ask your instructor. And again, for my students, the intelligent design material won't be on the test, but if you have questions, ask me about it.